Welcome back to part 2 of the lecture 12, Lattice Boltzmann, of the High Performance Computing Advanced Scientific Computing course. In second part, we will talk about the Lattice Boltzmann method. Boltzmann equation, it's derived by Edward Boltzmann, Austrian physicist who made many major contributions to statistical mechanics and thermodynamics. Well, Boltzmann derived an equation for the change of the distribution of energy among atoms due to atomic collision and laid the foundations of statistical mechanics. Boltzmann was also one of the first continental scientists to recognize the importance of the electromagnetic theory proposed by Maxwell. Well, it was a tragedy that Boltzmann did not see the glory of his pioneering ideas. The Boltzmann theory achieved the deserved breakthrough and acceptance among scientists only shortly after his death, with help of Max Planck and Albert Einstein. In this part, we will talk about its equation and how a lattice Boltzmann is a great alternative for traditional CFD in fluid dynamic area. To have a visualization and description for the lattice Boltzmann method, if we look on these figures here, there is a collision and propagation. First, in pre-collision, there is a condition of the distributed function, and then after the post-collision, then we have the post-propagation and what the condition of the function, as you can see here in these steps. Well, Boltzmann equation is proposed in 1872. It's explored the probability distribution function based on the particle collision, which is the most important achievement in the 19th century. If we want to determine this equation, it's basically on the probability distribution function, which is called f here. It's quantity of the particle at time t between two locations, which is called x and x plus dx, with momentum p plus dp and p. Instead of the momentum, we can use the velocity as well. If there is an external force on the particle, the momentum p will change to p plus dp and location from x to x plus dx. Quantity of particles stay equal before and after the external force act because of the conservation, if there was not collision. If collision happened, there will be different in the quantity of particle before and after the collision. These different statement of the collision, the concept of the lattice Boltzmann method. And in the next slide, we will see how it's working and how we apply it to solve this fluid dynamic problem or other problems. Let's go through in detail on the collision and what's happening in the lattice Boltzmann method equation. If we assume between the particle there is not collision, without collision, that probability distribution function, it will be same between two time and the location if there is not collision. But if we have a collision, the probability distribution function will be different. And this difference between this function between two location and time step, it will be a function, which is commonly called Boltzmann equation here. And the main requirement to solve this problem, this function or operator to solve the Boltzmann equation, as you can see here. If the neglect external forces and normalize the mass to 1, then in the equation P it will be equal to C, which is C the set of vector to tile the entire space, such as hexagonal tiling. And this CI, it's called lattice velocity or Boltzmann velocity. We will look on these in the next slide, and we can see this is the probability of the velocity for every particle on the hexagonal structure. Based on Maxwell theory, it doesn't matter to study the individual particle behavior. If we have ability to study the probability particle availability, it will be matter and we can understand the feature or properties. So the probability distribution function is definition in this concept. If we look on the probability distribution function for the particle, it will be three independent variables: position, time, and momentum. Instead of momentum, we can use the velocity. The vector features is they have three components. So three component position, three component momentum, and the time is a scalar value. So we have 7 variables. As we said, there are two fundamental concepts, collision and streaming. And if we look on the equation, what's happening in the collision and the streaming, and the difference between these situations. We said we have the external force, and usually it's assumed zero or neglected. So the equation for the Boltzmann, this is the structure for the Boltzmann equation. The equation has not microscopic properties such as viscosity, heat transfer, etc. Then if f, which is the distribution function, probability distribution function, change via the collision, the probability distribution for the particle is changed as a result of the collision. In this equation, let's look on the available parameter here. This function, if we don't have collision, it will be zero, as we said. In such condition, for a very dilute fluid, very less density, very few particles, and for Knudsen over than 10, which particle without interaction, we can have this assumption and use it for the solution. But in the most cases, we need we have the collision, so there is a function here or operator to required to solve the Lattice Boltzmann equation. When we look on this function, is based on the probability distribution function. F is a function of particle, which is we can say is molecular behavior. Then how we can extract the microscope properties from the Boltzmann method? The answer is conservative laws. So we can apply the conservative laws, and we can see here how we can apply the conservative laws, and we extract the mass with this equation. We can extract the momentum with this equation. We can extract the energy. Also the velocity, relative flow velocity by this equation, and this is the energy of the microscopic as of microscopic properties. So it's important to find these function or operator and how we can solve it. To define this function, we have Maxwell-Boltzmann distribution. As you can see here, this equation. F equal is a local equilibrium value for the population of particle in the direction of the specified link. So it's based off this concept. There is a BGK operator proposed in 1954, and it's suggesting this function equal to F equal minus F over tau, which is term tau is the relaxation time and related to the viscosity. There is a specific equation for this value, we can calculate it. Then when we have this function, we can solve the Boltzmann equation, and we can have the solution for the domain of the problem. Regarding the lattice Boltzmann equation, there is a Chapman and Solkov theory, which provides the framework in which equation of the hydrodynamic for gas, that means Navier-Stokes, can be derived from the Boltzmann equation. So there is a both direction between the Boltzmann equation and Navier-Stokes, and these present us and as a evidence which this Boltzmann equation can cover the Navier-Stokes equation in the fluid dynamic area. When we look on the lattice Boltzmann method, there are some advantage, some disadvantage, and some limitation. The lattice Boltzmann method, a class of the microscopic particle based on the approaches to simulate fluid flow, they are becoming a serious alternative to traditional method in the CFD. LBM are especially well suited for simulate flow around complex geometries. They are straightforwardly implemented on parallel machines. So this is the part that related to parallel computing. Then we have evidence and determination that Lattice Boltzmann is working very good with the parallel computing. It can be shown that the lattice gases solve the Navier-Stokes equation of fluid flow, which we said there is a theory about it. When we look on the lattice Boltzmann and we compare it with the traditional computational fluid dynamics, we can say the Navier-Stokes equation solution for incompressible flow. However, detachable calculation, two steps in the lattice Boltzmann collision and streaming. It's useful in the HPC. We have fast solution and low cost. We don't need to have a stability consideration in the LBM, like as usual we are doing on the CFD method. Navier-Stokes required continuity, but LBM not. We are dealing with particles. The code is simple because it's for the particles. The displacement term in the lattice Boltzmann is linear, which is different from the Navier-Stokes equation. The limitation in this method, modeling gas-liquid multiphase flow with density difference or high viscosity difference between phases is still difficult. However, there are many ongoing research and there are some achievement which seem these limitation will reduce, and it will has a capability. It will have a capability to apply in this area. To simulating the streams with the high Mach number, it's still facing some obstacle. And modeling geometries with curved borders, it required more focus and overcome on some limitation. The most application on the lattice Boltzmann, which is difficult to solve by the traditional CFD, the porous media, the turbulence flow, multiphase, and reactive flow. So the capability and power of the lattice Boltzmann, it's in the good level, and in most application that we can use the traditional CFD, it could be helpful to do that. Additionally, the capability to apply the high performance computing in this method make it possible to use it for large and big problem in the fluid dynamic area. If we want to see the difference between the solver for the lattice Boltzmann method and Navier-Stokes, we can have this comparison. In the lattice Boltzmann method, LBM discretize the domain of the LBM. It's lead to first order of the partial differential equation, PDEs. But in the Navier-Stokes equation, we have the second order PDEs. In LBM, the convection term is linear. However, in the Navier-Stokes, this term of convection is nonlinear. In the LBM, the pressure can obtain via the states equation, but in the Navier-Stokes equation, For incompressible flow, the pressure must be obtained from the Poisson equation. In the Navier-Stokes equation, we need to calculate the identification factor, which is called CFL, Courant, Friedrich, and Lewy, to meet the condition, but in the LBM it's always equal to 1. With LBM, we can have a molecular interaction and simulate them, but in the Navier-Stokes it's not possible. However, the boundary condition in LBM need to develop, and still for some problem, the boundary condition could not be defined to solve the lattice Boltzmann, especially when there is a curve domain. For Navier-Stokes equation, it's essential to have the boundary condition, initial condition. LBM has explicit and without iteration solver, but in the Navier-Stokes, the iteration must be converged to find the correct solution. Regarding the application of Lattice Boltzmann method, LBM, and the computing, there is a model to discretize the domain of the problem, which is basically a state of each particle in each time step is dependent on the neighbor particles. These lead to update of the properties to be local, and it's reducing the computing slot and time. The type of the model is matter, indeed, to solve the domain in the LBM. One of the well-known model to discretize the domain of the problem in the LBM is called dxqy, which x the dimension of the model and y the number of the particle vectors. One of the two-dimension model is d2q9, which is 2 is the dimension and 9 is the component of the velocity vectors. In this slide, you can see example of the discretization of the domain by this model and the single model how it look like. There is a 9 component of the velocity in this model, and you can see the direction and how they labeled for every direction. This is the example of the Lattice Boltzmann method application, which they evaluated the performance of the Lattice Boltzmann method for fluid simulation on the particular processor. As you can see, they made the weak scaling with different model of the discretization model in these figure. You can see 3 different 3D model: D3Q15, D3Q19, D3Q27, and it's with increasing number of the node, it provides the weak scaling. And here as well, again, they use these models with different number of the ampere processor, 1 ampere and 4 ampere processor, and it's presenting how the scaling working and which one the ideal scaling and how it's working in the real application of Lattice Boltzmann. The capability of the Lattice Boltzmann is in the recent study presented good result, and however in some problem and some domain, because of the difficulty to determine the boundary condition, still there are some obstacles. But for applicable problem or some problem that they are in the traditional CFD consuming higher computing, with the Lattice Boltzmann, it seems the good perspective available to solve this type of the problems. This is the another example of the sedimentation of an elliptical cylinder example. In this problem, there is an elliptical cylinder falling in the closed narrow domain, and the coordinate is specified in the problem here. As you can see, the simulation of this problem with lattice Boltzmann provide very good result and detail. As you can see, the Reynolds number is 32.9, and it's presenting detail of this falling of this elliptical cylinder with good detail. Here we finish the second part of this lecture regarding the lattice Boltzmann method, which is really powerful alternative method for computational flight dynamics. Of course, the detail of the lattice Boltzmann, it could not be presented in one lecture. It could be in not only one course. Maybe you need to have a few courses to learn the detail about this method. However, there are many ongoing research on the lattice Boltzmann method, and there are many references, videos, books, and papers. If you are interested in this method, you can read about them. In this course, since we are mostly focused on the high performance computing, one of the advantage of the lattice Boltzmann method is application of the high performance computing and its matching in a really good manner in this application. So it seems if we apply the lattice Boltzmann for a very large problem, it's matching in the computation with help of the high performance computing with good cost of the computing. From the recent literature, it's always cheaper than the traditional CFD. However, there are some limits to solve some problem, and hopefully in the future the scientists and the researchers, they will all come on many of these obstacles, and we can apply lattice Boltzmann widely in many problem, and with help of the high performance computing we can have a new achievement in some difficult problem like turbulent flow and other type of the fluid dynamics area. In the last part of this lecture, there is a video. It's introduction to lattice Boltzmann method, and it's presenting the scales we talked in the first part, microscopic, mesoscopic, and macroscopic scale, and you can see how they are connected each other in different scale. I suggest you watch this video, and here we finish this lecture. Here are the references in this lecture. There are some good introduction book for the lattice Boltzmann. If you're interested, you can look on them, and there are some references. And thank you for your attention. Thank you, and see you in the next lecture.